Matrix, and welcome to yet another exciting show of Matrix. My name is Luni, and today we're focusing on your exam guide for physical science. So do hit us up on all our social media platforms. All you need to do is search for Matrix, as well as our WhatsApp line, and I'll leave all of the details on the screen for you guys. We've got cool competitions going on, guys, so please stay tuned to get all of those details. But as always, I'm never alone. With me are my awesome sign language interpreter, Nicolene, as well as our cool teacher, Temba. Thank you so much, guys. Over to you.
Thank you very much, Luni. Welcome, guys, to our physical science focus session. Today we'll be basically looking into the physics, which is paper 1, as it has been already indicated. But also, what is very key in today's session is that we particularly going to focus mainly on the strategies, the main approaches to the problems that have to do with the physics paper. Just a brief look into the paper itself, right? Okay, the physical science paper 1, what exactly does the paper look like? Okay, the duration of the paper is actually 3 hours. So this actually involves all the time for the section A as well as the section B. The total marks is 150 marks, right? Now, having said that, the two sections that make up the paper is section A, which is based on the multiple choice questions, right? A lot, I think, needs to be done as far as the multiple choice questions are concerned, in terms of readiness, in terms of the preparation. And then secondly, we have section B, which are long or structured questions, okay? So these are long questions, okay? Right. So this is basically the layout of the paper. But let's delve deeper into the bolts and nuts of what exactly entails our paper 1. Okay. So the section A, which is the multiple choice, okay, 4 options will obviously be provided, but it takes a bit of skill, and a lot of thinking, a lot of application. Not all the multiple choice questions are based on recall. So the total number of marks is 20 marks. Now, if a question is 20 marks, it says one has to allocate, a decent amount of time in terms of, trying to respond to those questions, because there are different levels. There are a lot of skills that are involved as far as multiple choice. Not only does it involve definitions, it has also a lot to do with, the conceptual understanding, particularly with the physics. You'd realize, I think, as you are busy with your exam prep, after the trial now, we're doing a lot of question papers. You'd realize there's not so much of the calculations. It's about the understanding. You talk about an object of mass m. It's moving at a speed v, So the idea is set around the concept in itself, not so much about the numerical values that are involved in calculations, right? And then all topics are definitely going to be assessed. So we've got the mechanics, we've got wave, sound, and light, we've got electricity and magnetism. So all the topics are covered in the 10 questions of the multiple choice, okay? Right. Okay, moving along, then we've got the section B, which are long questions or structured questions. One more thing that is very, very important, remember, with the physics or the chemistry, physical sciences, that is, we do not have an option to actually choose questions. All questions are compulsory. So it says a lot has to go in terms of preparing, in terms of the level of readiness into the exam itself. So section B is 130 marks, okay? So the 130 marks, if you add it to the 20 of the first section, it will definitely give us the total of 150, right? So each one of these topics, they definitely carry, different weight, which contributes to the grand total of 150. Now let's quickly look into, the knowledge areas or the topics as far as the number of marks that each one of them carries, right? So we've got the mechanics that is broken down into your Newton's laws. It's your Newton first, second, third, as well as the universal gravitation. We also have questions based on vertical projectile motion, linear momentum, as well as work, energy, and power. And then under waves, sound, and light, we definitely going to look at, topics like the Doppler effect. But now, if you look at the mark allocation for the mechanics, we've mentioned about 4 broad categories that make up the mechanics section. Okay, now the total of the mechanics is actually 63 marks, give or take, plus minus. Now, if by comparison, you immediately pick that up to say, okay, mechanics actually carries the greatest weight in the physics paper, right? And then we've got electricity and magnetism. Now, as far as electricity and magnetism, something that I've briefly touched on has to do with the work that we cover in grade 10, 11, culminating into, the major concept in grade 12. When you look at electric circuits, we start electric circuits way beyond grade 10. We also have to do some work on electrostatics. We talk about fields, in grade 11, where we talk about point charges. We talk about the quantization of charge, which is a particular area which is a problem, as far as the paper 1 is concerned. But at a later stage, we'll definitely look into the detail of that, okay? And then last but not least, we've got matter and material, which is based on the photoelectric effect, right? Okay? Now let's look at the tips, because we have indicated earlier that the main focus of our session today is to look at the main strategies, the tips. What is it that we need to do in terms of time management during and while we prepare for the examination? All right. Now, you need to plan your reading time very carefully, okay? This is inclusive of both the preparation and while you are in the exam, okay? So time is a major factor as far as exam prep is concerned. And then also, we need to allocate adequate time to each question. What that simply means, you'd remember, if a test is out of 50, you need, give or take, plus minus an hour for that. So a question that has got a lot of marks, you need to allocate correspondingly, a longer period of time. But it should be within the 3 hours in total, okay? Right. Another look at, the questions that have got implications as far as the experiment, practical investigation is a common feature in the physical sciences exam. Now, the 3 variables that are very important are those 3, which is the independent, dependent, and the control variable. Also remember to polish up on the investigative question in as far as the punctuation is concerned. Right. Now, a brief look at the graph work that has to do with the mathematical skills. And, in most cases, it could be based on experiments. It could have been based on, theoretical values that are given in terms of, an investigation that was carried out. Now, part of the skills that are necessary is it has to do with the graphs. Now, you need to be in a position to plot or sketch. These are 2 different, aspects of the graph. As far as plotting, it has to do with a set of data or a table of results that may be given, obtained from an experiment or an investigation. So when you plot, you use actually a grid, and you use a suitable scale, and all the key components of the graph need to be well covered there, because there are marks for that. But when you look at a sketch basically shows the relationship. It could be a linear, which is directly proportional or inversely proportional, without any, specific focus on the scaling. And then in the case where a graph is given, that skill of interpretation, I think, becomes very key at that time. And it simply means that you'll be given a graph in a grid, and then you are supposed to use the graph to respond to questions. And in some cases, the examiner will say, by using the graph, decide or calculate, draw conclusions. So these are some of the very important skills that you need to polish leading to the final examinations. Luni, for now, over to you.
Thank you, Timba. Guys, we're going to take a quick break, but don't go anywhere. We'll see you straight after this. Welcome back from the break, Matrix. Thank you so much for joining us. If you've just tuned in, we are doing your exam guide to help you prep for the upcoming exam. And like I said, guys, we've got a competition. So if you're someone who's constantly running out of data and you can't go online to check any of the content that we've created for you, this next competition is just for you. Wazomatrix is bringing you #WazoWinner competition, where 2 matrics stand a chance to win 2 gigs of data. I'll give you all of the details on the screen, and head on over to our Facebook page to take part in the competition. So enough talking from me, over to Temba.
Now, a brief look into the exam strategy in terms of, responding to different questions, right? Now, you need to learn your definitions very well. Now, definitions, they form a major proportion of, more than 30% of the marks in the total of 150. The definitions need to be extracted from the exam guidelines, okay? So the exam guideline is the most important tool for us to understand our definition. So these keywords that are in definitions, you may highlight them, but what is also important is that with definitions is either you get 2 out of 2 or 0 out of 2, right? In this case, just to emphasize on that, the keywords in the most important definitions need to be captured and be used in the correct context. What that simply means is that if you write a definition, it should make scientific sense. Not only do you have the keywords, put in the definition, but they must be in the right place to convey the correct scientific meaning. All right. And then also the data sheet is one of the very important tools that you need to familiarize yourselves with. Most of the laws, concepts are captured in the data sheet, mathematically that is. So the examiner would say define in words. Let's say for argument's sake, P is equals to mv. And when you define linear momentum of an object, it's actually the product of mass and velocity of an object. And if you look at the mathematical, formula or equation, it captures that on the right-hand side. So the data sheet is a valuable, resource in terms of remembering these definitions. We also need to pay careful attention to the mark allocation. Okay, so if a question, say for argument's sake, is based on a calculation, and let's say it's 3 marks, it means it's a routine calculation. So routine calculation, what exactly does it involve? It involves identifying the correct formula, right? Identify the correct formula, right? So this formula needs to be copied as it is from the data sheet. Okay, there's no need whatsoever for you to try and change the subject, because in the process a lot can happen. But and please don't waste time. You don't have to do that. You just copy the formula as it is given, and marks will actually be credited for identifying the correct formula. And then when it comes to substitution, right? Pay careful attention, grade 12s, to the fact that some of the values of the quantities that are given that you need for the substitution may not necessarily be in SI units. So the SI unit is what you substitute into the equation. So if there is a need, where necessary, you need to do the conversions, say for argument's sake, from microcoulombs to coulombs, okay, milliamperes to to amperes. These are just some of the examples that come to mind. And then the most important one, the free body diagrams. When you talk of the free body diagrams, you'd remember that most of all these mechanics questions are based on forces. Okay, we've mentioned linear momentum and impulse, work, energy, and power, vertical projectile motion, Newton's laws. It has to do with the forces. And even electrostatics, we talk about, electrostatic force exerted by one point charge on another. It's all about the forces. So forces are essentially vectors. So what's so important about vectors, as we would recall it from our grade 10, is that vectors have got a component of direction, something which is often, overlooked, and you'll be penalized at the end of the year if you don't pay careful attention to the vector nature of the forces. So when you draw free body diagrams, you need to indicate the forces, label them correct, make sure that the tail touches the dot, okay? But more importantly, there is a distinction or difference between a free body diagram and a force diagram. And the examiner will be very, very specific in that case to say, in this question, you are required to draw a free body diagram or just a vector diagram. So that's something that we need to definitely visit. All right. Okay. Now let's look at a typical, topic which is often also a problem, but with our emphasis on this topic, it's actually on some of the strategies, as an example. Vertical projectile motion, okay? What is important about VPM? Okay, we'll summarize it as VPM, okay, which stands for vertical projectile motion. Now, the definitions, as we have indicated in the previous slide, that are very important. So what's so important about our direction is that a lot of quantities involved in vertical projectile motion are actually vectors. That's your acceleration, that's your velocity, that's your change of position, which is your displacement. Usually, if we say vertical, we'll obviously talk about delta Y, okay? So take note of that as well. But the main idea behind free-falling objects or vertical projectile motion is that there is a constant acceleration that is experienced by the object. So, I would use this statement just to capture exactly what is important about free fall and projectile, because those are the two very important terms that are most likely to be asked to define in terms of definition. Okay, a projectile is an object, right? And then free fall is a type of motion. So maybe just to summarize that, we would say a projectile undergoes free fall. Now, this is an object which undergoes free fall in the sense that only the force of gravity. Now, speaking of force of gravity, now there is a difference, again, matrix, between gravity and force of gravity, all right? One is a consequence of the other, okay? So if you think of it in terms of, the universal gravitation, the Earth tends to pull objects towards its center. So the force exerted by the center of the Earth on the object is the force of gravity. That is due to gravity. That's why the object accelerates vertically downwards. All right. Now, sketching a free body diagram for a free-falling object. Now, one of the things that we must also indicate is that as far as free fall is concerned, by the virtue of the fact that the only force acting on the object during free fall is the force of gravity, not G, is the force of gravity. Sometimes we describe it in terms of the weight, right? Now, this is the only force. So the number of marks that are allocated for the free body diagram is also an indication of the number of forces that you actually have to indicate, right? Now, the context of questions are very different. So every scenario is unique in its own special way. So read the information carefully and identify what is given. So collect the data, right? While doing so, take note of the direction, right? Because as far as direction is concerned, because these are vectors, so it has got far-reaching implications in terms of calculations, okay? Now, you also need to identify the correct equation of motion. This is also provided in the data sheet, all right? And then make sure that you understand and state or define the direction from the onset. Say, for argument's sake, if you say take upwards as positive, you're going to maintain that throughout the entire long question. So you don't change every now and again. You become consistent. So if you, for argument's sake, you throw an object up, we'll look at a particular example like that in the next slide, okay? Make sure that you immediately say, if you say upwards is positive, meaning your acceleration will be negative, which is downwards, okay? Now, also revise graphs of motion for a projectile. So these are different scenarios. It can be an object released, thrown, dropped, pay careful attention to the words because they've got scientific implications in terms of what exactly happens as far as that particular motion is concerned. All right, okay, right. These are some of the common errors that are involved as far as vertical projectile motion. We need to guard against that because marks can be lost in that way. Now, define the terms correctly, okay? Also, in referring to the force that acts on the projectile, which is the force of gravity, we've mentioned that we are not going to use the word gravity we would use the force of gravity or alternatively weight, because the two terms can be used interchangeably to refer to one and the same thing, okay? So in calculations, some candidates, they continue to say acceleration is 0 at the highest position, right? The main thing that we've also indicated as far as free fall is that the acceleration remains constant in both magnitude as well as direction. So there is no way that acceleration will change from 9.8 meters per second squared downwards to 0. So if we say it's constant, it means it does not change. Okay, that's the big idea in as far as vertical projectile motion is concerned. Okay, now the use of signs to indicate direction is one of the problem areas. Okay, so you define your direction, you choose your direction, you state it clear from the onset, and you maintain that. Okay, right. So while substitution is being carried out, take note that in physics, the negative suggests the opposite of the direction that we chose as positive from the onset. So there is no way we are saying that minus 5 meters per second is slower than 5 meters per second. It's equal magnitude, however, in opposite directions, right? And then in the case of an object that is, say, for argument's sake, thrown vertically upwards, right? And that object reaches the highest position. This is just a scenario that we would want to use as an example. Okay, the moment you say the term ignore effects of air resistance, that has implications as far as the type of motion that the object undergoes. So we have a scenario here without concentration on the actual questions. Let's understand the basics. If you throw an object up, okay, that object experiences the force of gravity only. It slows down uniformly. Hence, we are saying that the acceleration remains constant. It reaches the highest position and then moves faster and faster going down. Now, in both cases, the object experiences a constant acceleration because as it slows down uniformly going up, it's actually accelerating downwards in the direction of the net force, which is Fg. That's one application of the Newton's laws as far as VPM is concerned. Now, speaking of graphs, which is very, very important, okay? The moment the examiner says air friction is ignored, let's understand that that implies a free-falling object, and that object is a projectile, okay? So in the case of that object which was thrown, it could be a tennis ball, it could be anything, all right? So that object is a projectile, we're fine with that, and we're saying that a projectile undergoes free fall, the acceleration remains constant. Guys, these are the key ideas that make up, VPM in this question. Now, let's say for argument's sake we were to consider a graph of V versus T of an object that is thrown vertically upwards, right? For the mere fact that the object changes direction, it means we would need the two quadrants. Now, if, say for argument's sake, it could be prescribed, the object is thrown upwards, and then we're saying upwards is positive. So as it slows down, this object actually will get a graph of this sort. Now, I want you guys to pay careful attention to the length of time that it took for the upward motion. So the first part, if I say this is A to B, and then to position C for argument's sake, the length of time that it took the object to actually reach the highest position is shorter than the actual motion for the downward movement of the ball. Now, this gradient of the graph, that's another mathematical skill. We also spoke about y is equals to mx plus c earlier, right, to say there's a mathematical relationship. Now, the gradient in this case, which is actually change in velocity per unit time, is an indication of the magnitude of acceleration, all right? Now, you'd realize that because this is a linear graph, then the gradient is constant. Hence, we are saying that this object experiences a constant acceleration, right? Now, the examiner may ask anything based on velocity versus time, acceleration versus time, position versus time. So, but the understanding in terms of the uniqueness of the scenario is also very important. Say, for argument's sake, we speak of the acceleration versus time. We would understand that the acceleration remains constant. Now, in this case, we chose upwards to be positive. So we've got acceleration in meters per second squared on the vertical axis, and then we've got the time on the horizontal axis. Now, because we took upwards as positive, and clearly from this graph, you can tell that this has got a negative slope, then our graph will be below, which will be negative 9.8 meters per second squared, and then we get a horizontal graph like that. The horizontal suggests that the acceleration remains, constant in both magnitude and direction. Dolly, over to you for now.
Thank you, Timba. Guys, we are going to take a quick break, but before we do, don't forget to hit us up on our social media pages. Just search for Wazimatrix, as well as enter that competition. Send us your questions and comments, as well as hit us up on our WhatsApp line. We'll see you straight after the break. Welcome back from the break, guys. Thank you so much for joining us. As always, we've got a WhatsApp question, so we're going to have a look at that.
How do you answer electrostatic questions when you're asked what happens to the force if you change the charge and distance between charges?
Right, it's a wonderful question that has a lot to do with the basics of electrostatics. Now, let's quickly look at some of the key things that we need to consider as far as, because this has to do with the Coulomb's law. It's important for us to identify the concept involved in the question. So once it talks about the forces, and the distance of the charges, we need to classify that question under a particular concept. So we appreciate the fact that this is about the Coulomb's law, essentially, right? And then what are some of the most important things in response to this very generic question is that you need not to forget that when we talk about Coulomb's law, we are talking about the electrostatic force. So the electrostatic force is a vector, right? So direction needs to be taken into account always. And remember, every force is applied on a particle or an object by another, okay? So the direction becomes very crucial. Now, also make sure that you learn the Coulomb's law. We have mentioned the importance of the examination guidelines. So in the formula sheet, it will be written F is equals to K, Q1, Q2 over R squared. So the mathematical equation captures, even the relationship that exists between the product of the charges as well as the electrostatic force, as well as the square of the distance between those charges and the electrostatic force, right? So the key words, directly proportional, inversely proportional, but do not forget that this is about the square of the distance between the charges. But also, there is a thin line between the Coulomb's law and the universal gravitation. Now, in what way? The very same skills that in response to this question to say what happens to the force when the charges are doubled or whatever changes are made onto the charges as well as the distance, we need to recognize that this is the very same skill we would apply it with the universal gravitation law. But however, the most important thing that the examiner will penalize if you do not include as far as the universal gravitation is that we talk about the distance, the square of the distance between the centers. Well, for particles which are actually minute, so we can even ignore the radius or the diameter. So, but as far as the universal gravitation, the distance, the square of the distance is actually between the centers. All right, okay? Now, the understanding also of the field is very important because in an electric field, another charge will experience an electrostatic force. So while we speak about the electric field, we are also talking about forces. So we are not running away from the vectors once again. Hence we said as long as there are forces and vectors, direction becomes a very key component of that. Okay, so understand that a field is a region in space. Okay, grade 12, you need to distinguish between electric field at a point and electric field. So a region in space is just a field, okay? But if we talk about electric field in strength, we're talking about the force that will be experienced per unit positive charge. So force, okay, per unit positive charge, right? per unit positive charge. So if we talk of a unit positive charge, we are actually talking about a test charge, which is actually the 1 coulomb of charge, which is positive. All right, okay? Right, so that's the unit positive charge, which is, so even the formula, F E is equals to F over Q. This is given in the data sheet. This is actually the definition in terms of the magnitude of the force experienced by a test charge in a field, okay? But in terms of calculation, we'll talk about a charge Q that creates the field, okay? Now, the distance from the surface of that charge which creates the field, and we square it, is the one that we actually consider as far as electric field strength. So sometimes we'll refer to it as electric field strength or electric field at a point. So these are some of the, the general stuff that we need to polish up. But also in grade 10, we looked at electric field patterns, in terms of magnets in grade 10. And then in grade 11, we also looked at, point charges in space. So when we talk about a point charge, then we know that around that point charge, what exists is actually an electric field, and we use electric field lines. So 3-mark questions are usually asked as far as electric fields at a point. So in some cases, you'd consider the field between 2 point charges, either like or opposite charges. So those are some of the legal things. So in the examination guidelines, you'd have your checklist to say, okay, do I still remember this? If not, what do I need to do about it? Let me revisit and consolidate that as well. All right. And then that's a brilliant question that was asked. But here's another typical example of a question. It says, consider the charges X, Y, and Z with the same magnitude. So these are identical charges in a true sense. This word will be used quite often. Identical, meaning that it could be identical spheres, meaning they have the same shape, size, but necessarily they don't carry the same charge. They may carry the same charge or they may not. But if they're saying these are identical charges, it means the magnitude of the charge of X equals to that of Y equals to that of Z. The other ones are positive, which is the X and Z, while Y is negative. Now, let's look at the issue of the forces as an example. It says charge X exerts a force F on charge Y. Now, if you look at X and Y, they are at a distance R. So we have recognized that the concept involved in this question is actually the Coulomb's law, which says F is equals to K QX QY over R squared. So this is F. This is what is on the right-hand side actually represents F. All right? Now, calculate the magnitude and direction of the force that Z exerts on Y. Now, what's the difference between between Y and Z is that the distance has been doubled, but the magnitude of the charges is the same. Okay? For never mind, Y and Z will experience a force of attraction just like X and Y because these are typically opposite charges. Now, if we double the distance, what will happen? Then it says this is equals to K, Q, Y, QZ over 2R. Now, it's the square of 2R. That was the catch. It's the square of 2R. So if we double 2R, this will be like 1 over 4 K, Q, Y, QZ over R squared. So if that represents F, it means now the new force would actually be a quarter of F. So similarly, that's what you'd even do as far as the masses in universal gravitation law is concerned. Okay, right. And then it goes on further to say, find the force that charge Z exerts on charge Y in terms of F. Okay, so if we double the distance, because we know that the electrostatic force is actually inversely proportional to the square of the distance. It means then, from the calculations that we've done on the previous slide, we know that the new force, the charge by Y on Z, okay, charge by Y on Z, okay, is equals to a quarter of the original charge. So because we've doubled the distance, okay? All right. And then as far as electric fields is concerned, Also, vectors are heavily involved because we're saying that electric field at a point is the force experienced per unit positive charge. Take note of the small letter Q. It's not the big charge that creates the field. That's actually the test charge. This is a unit positive charge. Okay? That's our unit positive charge. Okay? Which is the +1 coulomb. Take note of that. So in the definition of electric field at a point, you need to clearly state that this is the force experienced by a unit positive charge, which is why the SI unit is then in Newton per coulomb. So if we talk about per coulomb, we're talking about a 1 coulomb of charge. Okay? So we also need to be able to determine the electric field strength at Z if the charge on Q is doubled. Okay, now, if Z creates, if Q is the charge that creates the field, so E is equals to K Q over R squared. Now, you'd realize that we even talk about the square of the distance between the point and the surface that creates the surface of the charge that creates the field. Okay, so you square the distance, so it's inversely proportional to the square of the distance, while E still remains directly proportional to the charge. So if we double the charge that creates the field, E will also be doubled. If we double the distance, remember, it's about the square of the distance. It will be 4 times as big. If we have the distance, it will be 4 times as big. So we use more or less a similar approach, right? Now, just to use a specific example in terms of the layout of that question. So here is Q, the charge that creates the field. Okay, X is a point. So it's very important. X, that's where we place at X. That's where we place the test charge. Okay. Now, if Q, say for argument's sake, is positive, all right? If Q is positive and then we place a test charge at X, obviously Q exerts a force on the test charge away from Q, right? Now, if we place the test charge, let's say at Z, okay, obviously the field strength is stronger at Z compared to Y. One of the things that we also mentioned in grade 11 is that the electric field line density is an indication of the strength of the field at that particular point. Because this is a positive charge that creates the field, the direction of the field is away. So that's another thing that we also need to remember. So as a result, if we place the test charge at a shorter distance, the field is stronger. Even the density of the electric field lines is indicative of that. So if we say, for argument's sake, we double the charge, then if E is equals to K, Q, let's say we double the charge, okay, now it becomes 2Q. That's the mathematical language. And let's say maybe this distance is a quarter of what it was. Then over 1R over 4 squared. Okay? Now, if we do the maths, you'd realize that we've got 2KQ over R squared over 16. Okay? So this is as good as saying 2KQ over R squared times 16. This is actually 2 times 16, which is 32 E. So if we double the magnitude of the charge Q and put it at a distance that is actually a quarter the original one, which was at X. So this field is 32 times as stronger at point Z than at X. Right, very, very important concept there. Okay, but now the other questions may be based on electric field at a point in terms of the net. Sometimes it can be net electrostatic force at a point due to more than one charge in space. So the diagram below shows the charges positioned relative to B. The diagram shows 3 charges that are placed at a distance from each other in a straight line. So these are collinear. Now, if for argument's sake, we talk about point B, okay, and then we're saying at point B, we place a test charge. Okay, the test charge is always positive, remember, because that's a unit positive charge. Now, the force that it experiences due to this charge, let's call this charge Q2, Q2, let's call that Q1. So as a result, the force exerted by Q2 on the test charge at B is actually towards so this is E due to Q2, okay? Right? Now, if Q1 is positive, it will repel the test charge away from it. And then this is E due to Q1. So the vector nature of these quantities, your electrostatic force, your electric field at a point, is what we want to emphasize in as far as possible, okay? Now, having said that, it's also important for us to, in closing, to look at, the overall, tips as far as preparing for the exam is concerned. Remember, the exam guideline, I think we've mentioned this, one too many times. Make use of the data sheet. This is always provided. Ensure that the conversion of units is covered, the direction dealing with vectors. And make sure, because this is physics, make sure that you interpret your answer. Due to time constraints, we can go on and on, but these are just examples, of some of the things that you need to revisit. For now, over to you, Lonnie.
Thank you, Themba, and Matrix, thank you so much for joining us and for engaging online. Don't forget to check out the schedules on www.wazamatrix.co.za so you can see when the next revision show will be playing. A big congratulations to all of the competition winners who will be announced straight after the show on the Facebook page. But for now, from me, Looney, Nicolene, as well as Themba, it's thank you and goodbye.
Siyabangena! Wazamatrix is back and better than ever, with catch-up lessons, revision and learning support on more platforms than ever before. There are great support materials on the DBE Cloud. Find us on television and revise 10 subjects. And if you miss something, relax, Ntwana. Go to our YouTube channel or DSTV catch-up. Need help? Check out Vele, our Telegram-based chat platform where teachers are waiting to help you. Prefer WhatsApp? Send questions or voice notes to our Wazamatrix WhatsApp line. And that's not all. Want to test yourself? Check out the Matric Live app. Hey Matrix 2021, we've got you covered. Confused where to go? Visit the Wazamatrix website at wazamatrix.co.za. Wazamatrix.